So I'm Alex Barrett, and yeah, as said, we're going to be talking about the NOAA-H project, which both Jack and I have been involved in. So this is a kind of interdisciplinary collaboration between three main parties. So the Open University, where I've been based, European Space Agency, where Jack is currently based, and a industry partner called CISIS, who were our computer science team. So Mark Woods, Spiros Karachalios, and others were involved in actually kind of the experimental parts of developing the machine learning networks that went behind all of this. I came in fairly early in the project as an expert geomorphologist to label lots of training data and basically combine make the training data set for this project. And that got me involved with them working with the output and producing other training data and other output data across the project. We then got Jack as an expert in geological planetary mapping to come in kind of sort of late once we had started having all these products to compile them into some nice geological maps, or pseudo geological maps, I think Jack would argue, or will argue, which we're going to be showing you in a bit. So Jack is now at ESA, who commissioned this work for the ExoMars landing site selection process, but moved there after working on NOAA-H. So without further ado, what does NOAA-H actually do? We had several objectives, both technical and scientific. So our scientific objectives tied into this landing site hazard assessment for ExoMars. We wanted to look at Oxia Planum and at the time Mawrth Vallis, which was being considered as the second possible site. Oxia was later selected. We wanted to look at these two sites and determine how easily traversable they'd be for the rover, how safe they'd be to land on, and consider things like the distribution of aeolian bed forms, which we're going to be talking about a fair bit later in the talk, and other sort of hazards or obstructions across these two sites. This allowed us to also do some science examining the aeolian environment of Oxia Planum and kind of speculating about the history that's formed these aeolian bed forms. And then on our sort of technical side, we wanted to basically see a proof of concept of whether this sort of stuff, which we'd normally do in GIS, could instead be done with AI. And the spoiler is that we basically come to the conclusion that AI can be a very valuable step in this process, but isn't a final arbiter. And certainly we're not going to be out of a job anytime soon. So what we're working on primarily is the HiRISE dataset. For any of you who don't know, HiRISE is our highest resolution orbital camera taking remote sensing images of the surface of Mars. So this is one of our 128-meter training framelets in which you can see some nice sort of fractured bedrock and some sort of brighter rocky bits poking up through this sort of non-bedrock drift material. There's more than 80,000 HiRISE images with coverage sort of sparsely across all of Mars. And this data set is amazing. It's fantastic. You can zoom right in, and it's equivalent to kind of looking at Earth in Google Earth scale, where you'd be able to see cars and tables and patios and things like that, if such things were found on Mars. But this does mean that it is a huge area and makes it quite daunting to actually survey large areas at HiRISE scale. Put things in perspective, here's a bit of Jezero crater. This is the fan deposits that Perseverance rover is currently making its way up. And here's that footprint superimposed upon the island of Manhattan to give you sort of a sense of how big an area on the ground just one sort of average sized HiRISE image covers. So this is why we're very much wanting a tool where we can feed in a raw HiRISE image such as this and get an AI to do a sort of first pass and tell us which of these areas are maybe bedrock, which of them might be kind of non-bedrock or aeolian material, some of these darker bits in this image. And NOAA-H, as it happens, can do that. So our ontology consists of two layers. We have 14 descriptive classes, which are textural classes defining different different kind of surface textures that you can distinguish in HiRISE images. So we go from sort of very smooth surfaces through to rougher ones, with the smoothest of all being interpreted as non-bedrock, while the slightly rougher ones are interpreted as several different bedrock classes. And by grouping these into these interpretive groups, we can train an AI which works entirely on a kind of descriptive basis, working only on the kind of information that's in the image, with no need for kind of context or interpretation. But then we can kind of come in and interpret that sort of as a second step of classification. What we've been largely interested in are the aeolian landforms. So in these little swatches, you'll see some of these in bigger images in a moment, are these kind of little sand ripples that form on the surface. And we've classified those at various different scales and in various different configurations. And of course, we've also trained it to look for areas of boulder covered ground, as those could be a major obstruction to either the movement of a rover or landing one on the surface. The result ends up being something like this. We feed in loads of different HiRISE images and get out classified masks covering each one. And then Jack and myself have painstakingly mosaic these into several map sheets, which have been published or are being published in the Journal of Maps. And for each site, this being Oxia Planum, which has been finally selected as the ExoMars landing site when that launches in 2028. The entire area in which the rover could land has now been classified with NOAA-H. You see the descriptive classes on one side, the interpretive groups on the other, and you can immediately see that the area is dominated by this kind of red-coloured bedrock, with smaller areas of non-bedrock material, which would be looser, less consolidated, potentially harder for the rover to drive over, kind of off to the sides. The aeolian stuff, which is definitely loose and unconsolidated, is confined to a few small craters or down in this valley down here, which are unlikely to pose too much of a hazard. But this sort of smaller aeolian material in the light blue here is sort of potentially more concerning, but equally rover trials that our group have kind of done in the field suggest that things on that scale should be easy enough to drive over. And the observations in situ in Jezero crater kind of bear that out. Once we have this data, we can do cool things with it, like here we've gridded up the area and calculated density statistics of features of interest, so we can see which areas have the biggest concentrations of ripple density, boulder density. But this does highlight potential areas where there may be kind of issues with the classification. We think that the kind of edge of this high boulder area here is too conveniently along a HiRISE boundary, and we think for some reason there's something about the illumination conditions in one of these HiRISE images where it's much easier to distinguish the boulders here and less so over here. So we've had to kind of do a few different tests, which Jack will be talking about in more detail, to kind of decide how much of this is a real reliable classification and how much of this do we very much need to be going in ourselves and verifying. And over to Jack.
Thanks very much, Alex. So like Indy said at the beginning, during our introduction, I'm Jack Wright. I'm a research fellow at the European Space Agency. But before I came here, I was a postdoc at the Open University for 4 months working on this NOAA-H project. And during the 4 months I was there, I was tasked with developing a workflow for creating those mosaics that Alex was showing you of Oxia Planum. And I developed the workflow by looking at Jezero crater, where we had 4 classified NOAA-H rasters. And the reason we had those is because we were curious to see if the machine learning algorithm could be transferred from where it had been trained in Oxia to Jezero, an area it hadn't seen before, and to see how well it would perform there. And so we had these 4 images, and the reason that they were interesting beyond that is because this is where the Perseverance rover landed, as Alex was saying, and as well as the Ingenuity helicopter. And we were really excited about the opportunity to use the data sets from these on-the-ground observers to fact check the classifications made by the AI. So if we go to the next slide, please, Alex. So in this slide, in the next one, I'm just going to show you some of these images from the Ingenuity helicopter on the right. And on the left, I show the NOAA-H classification of the same region. So starting on the left, we have an area that's mostly colored in this sort of burgundy color, and the colors are overlain transparently on a HiRISE image that gave rise to the classification. The little red dot shows where Ingenuity is in this image, the helicopter, and the red bracket gives an idea of the field of view of the image on the right. And you can see that the helicopter is hovering above some of Perseverance's rover tracks shown in yellow on the map on the left, and you can use them in the image to orient your eye. And you can see that the helicopter is hovering over a relatively flat surface with outcrops of this sort of flat-lying bedrock material that's sort of brighter in color, and you can see that it's highly fractured, and that corresponds to the burgundy color on the left. That's the color that represents the fractured bedrock class. You can see that it has a sort of scattering of loose material over it, but that NOAA-H is very good at recognizing the sort of the texture of this fractured bedrock, and it's classified this image really well. And you can see that this is a surface that the Perseverance rover has had no difficulty in traversing. So that's an interesting result from a rover traversability point of view. And then we can go to the next slide just to see another example of this. So here again, we've got another Ingenuity image on the right and a NOAA-H classification on the left. So the panel on the right is labeled E, and that means that you can look at the map on the left, and the red dot labeled E is the approximate location of the Ingenuity helicopter at the time the image on the right was taken. And you can see that the helicopter is hovering above material classified in green by NOAA-H, representing loose non-bedrock material, and in the image on the right, just underneath the helicopter, you can see that sort of loose non-bedrock material. And if you look sort of to the center right of that sort of lower part of the image, you might even be able to make out some of those aeolian bed forms that Alex was talking about earlier, wind-blown sand landforms that indicate that this is loose material rather than bedrock. And then sort of in the middle part of the image, you can see more of Perseverance's rover tracks going from left to right across the field of view, and you can see that in the map as well. The rover wandered into this more strongly textured material in the sort of center of the image, and then wandered back out of it again and proceeded off to the left of the image. And that region is classified in yellow on the left, which represents our sort of rugged bedrock class of surface texture. And you can see from the image that indeed this is an area that's very different from the foreground, which is sort of this featureless, almost textureless loose material, and it's much more textured rough bedrock in the sort of middle distance. And then in the far field, you might even be able to make out some more of these large aeolian ripples on the right-hand side of the flight path, shown in red, the red line on the left part of the image. Yeah, thank you for gesturing, Alex. And then to the left of the flight path, you can see that there's loose material that hasn't quite been organized into those sort of large aeolian bed forms. And NOAA-H has classified this as a sort of mishmash of different kinds of non-bedrock material. So here, there's quite a diverse landscape in terms of surface textures, and NOAA-H at this sort of outcrop scale has done a really good job of characterizing it. So if we'll go to the next slide, please, Alex. We can zoom right out and we can look at the full Jezero product. So on the left, we have the 4 NOAA-H classified HiRISE rasters of Jezero crater merged together into one sort of continuous mosaic. And on the right, to compare it with, we have a human-made geological map that more or less covers the same region, that was made with the same original data products, HiRISE images of Jezero crater. And this is a map made by the Perseverance rover team in preparation for the landing. And they wanted to characterize the landing site very carefully, as you can imagine. And they had a team of, I think it was something like 60 individual human mappers who divided this area into, 100 or more little mapping grid squares, and they each did a little piece, and then they all had to stitch it together at the end. And this was a process that took, many months, and it required a lot of training. And whereas it might interest you to know that on a good day, NOAA-H was able to classify one of these HiRISE images in about 15 minutes, certainly less than an hour, notwithstanding all of the training time that Alex had to put in to get it to that stage. So the product on the left, is with a trained NOAA-H was able to be produced in, less than a day, really, whereas the product on the right took much more time. And I think at this scale, what's striking is that the overall patterns between both products match each other very closely. I'm about to drill down into the detail of why we should be careful making such comparisons, but I just want you to walk away with the idea that it's actually done a pretty decent job here. There are some problems, however. The areas where it works quite well are with the non-bedrock, bedrock and large ripple interpretive groups, these groupings of similar and related textures that Alex was talking about earlier. But it works rather less well when we compare, for example, the boulder fields descriptive class that Alex mentioned earlier. The reason it doesn't compare very well is because the human mappers didn't map boulder fields. They mapped something that's kind of related, something called talus slopes. These are sort of steep slopes of material sort of around the toe, the distal parts of the delta. And boulders may be constituent parts of talus slopes, but they're not a one-to-one correspondence. And so that begins to explain why there are some mismatches between the two data products. And we can actually quantify that when we move to the next slide. Yep, nicely anticipated, Alex. This is an approximation of a confusion matrix where we compare the sort of the human geological made map, which we consider to be the expert classification of the region, against the performance of the machine learning algorithm. And the cells with values in the leading diagonal of this table should have the highest values, and ideally all of the non-leading diagonal cells should be 0 because they represent misclassifications. So if we focus on the non-bedrock, the bedrock, and the large ripples to begin with, you can see that where the human beings have classified a particular area as being non-bedrock, what is that? Something over 700 million pixels have been classified as non-bedrock by NOAA-H, which is an order of magnitude at least better than the other the numbers of pixels that were misclassified. It's even better for the bedrock, and the large ripples classes are also really good. So that's really promising for those interpretive groups, and we've got the precision and recall stats for those interpretive groups, and they're really good and promising results as well. It's less good for the small ripples, and probably the reason for this is that whenever human beings are mapping, they will, summarize the geological information in a region, and they will, gloss over these very small scale variations. But the NOAA-H classifies on the pixel scale. It retains all that information. And so where the human beings have glossed over a region, NOAA-H naturally includes a lot of interpretive group variation that will lead to these apparent misclassifications. They may not be misclassifications in reality. It's just a consequence of us comparing a human-made geological product that was made by people working independently for a different reason. And so it's not an apples and apples comparison, it's an apples and oranges comparison. And that was never more true than for the boulder fields and talus comparison, where we're trying to compare two basically completely different things that are somewhat related, but not really as closely related enough as we'd like for this to be a robust quantitative comparison. So please don't be disturbed by the very disappointing precision and recall values for that interpretive group. And then to finish off, we'll move on to the next couple of slides. I'll talk a bit more about the other things that the machine learning hasn't able to do quite so well. And I put these slides together for another talk where I was speaking to some anxious geologists who were concerned that they would be out of a job because machine learning would take it from them. But over the next couple of slides, I'll show you that any geologists in this group maybe don't need to worry just yet. For example, on this slide, I'm showing that the machine learning algorithm was transferred from a training data set in Oxia Planum to a geographically separated region with a different history in Jezero crater. And an interesting result is that the aeolian bed forms, the large ripples in Oxia Planum, had a more east-west trend to them, and in Jezero crater they had a more north-south trend, and yet the machine learning algorithm has been able to identify the ripples correctly in Jezero, despite their different orientation. Where it has come afoul is that sometimes there were little parasitic aeolian bed forms riding on the backs of these larger ripples, and that just made the crest geomorphology a little bit more complicated. That was a texture that wasn't in the training data set. So consequently, it got a bit confused and misclassified the crests of some of these ripples in yellow, which is the bedrock class. And a human can very quickly tell the difference between a pile of sand in an aeolian bed form and actual bedrock, whereas the machine learning algorithm has got confused here. And that's quite a serious misclassification. Fortunately, it wasn't very widely distributed, but nevertheless, it was something to bear in mind. And then if we go to the next slide, here's the real killer for AI with respect to its career in geology. It's purely descriptive of the surface textures, but it has no understanding that these textures are representations of 3D rock volumes that have some origin by some geological process. They don't understand that the 3D rock volumes can be interpolated under the surface and from one part of the map to another. And this is all something that human geomorphologists and geologists can do whenever they look at a surface. It can't produce a cross-section to tell you what's underneath, and it won't tell you the order in which these events that led to these different rock formations happened. And so these are all things that come out of the geological mapping process. On the right of this slide, I show some examples of these cross-sections where people are competing, debating within the team for their preferred hypothesis for the geological history of the region of Jezero crater. And if human beings are arguing with the limited evidence we have to distinguish between these events, which are mutually exclusive, the AI really doesn't have the contextual information to begin to even address these kinds of problems. And then I think my next slide is my final one before I hand back to Alex. The product on the left has a lot of pixel scale detail, but it isn't really human legible. I mean, a trained geologist can look at the geological map on the right and be able to begin to tell you, based on that two-dimensional representation, what's happening in the subsurface, what order events happened in. The AI doesn't understand these things. And so we think that a NOAA-H product is a good starting point for a human-led geological mapping campaign. It might be useful in sort of rover landing site characterization setting where we can quickly produce a first pass machine learning characterization of the landing site that we can feed to the team of 60 or more human geologists who then go and do the detail and the 3D reconstruction analysis. But nevertheless, these products are quite useful, as Alex was saying, for mapping out the major hazards for rover traversability, and in combination with the rover engineering specifications and topography, you can begin to build up a good picture of the trafficability of a rover landing site. So geologists, hopefully you still have your jobs, but we still think these products are really useful when all of their idiosyncrasies are taken into consideration. I'll hand over to Alex again.
Yes, I think we're getting a little short on time, so I will very quickly run through our last example, which is really just a sneak peek of the paper we've just submitted, and which should hopefully be joining these maps fairly soon. This is Mawrth Vallis, which was our other training area, the runner-up landing site for both ExoMars and I think both of NASA's last two Mars rover missions. And this is a useful site to compare because we have this beautiful descriptive classes product. But because it was so heavily examined, this site, as part of the landing site selection process, we also have some much more in-depth human mapping with which to compare. So the Mawrth Vallis is this channel along here, and our area is these sort of rocky mesas for the south of it. And while we were working on NOAA-H and putting together the training data set, our colleague Peter Forden was busy mapping all of these little patches of ripples by hand. So this area is kind of here in sort of the central region of the area that we've classified. And he went in and basically classified them into 100%, 50%, and 20% coverage on a much smaller scale than what the Stack et al. Group attempted in Jezero. We can kind of dive right into kind of the sort of small area scale and compare this with our NOAA-H output. So here's what Peter produced, with red showing areas where he thought there were continuous ripples, kind of in this small crater, orange being the kind of intermediate areas with around 50% coverage, and then the pale yellow being the areas with much more dispersed ripples. This is how a human goes about classifying this kind of terrain. With AI, we can much more rapidly do far more detailed mapping than a human geologist is capable of. And so in those areas which are kind of sparsely covered, we can try and isolate the individual large ripples and patches of small ones. So we capture much more detail, but as Jack was saying, is it useful detail? Well, it's definitely a very useful starting point. With this as a guide, we could very rapidly get to this kind of classification product. When we compare the metrics for these, we find a very kind of strong contrast between the areas classified by the human as continuous and those classified as discontinuous. In the continuous areas, we have very high recall, so it's finding almost everything that a human classified as continuous, but there's very low precision. So it's not doing very well at picking out just the areas which a human classified. It's finding a lot of the other very small continuous areas. And looking at it in the HiRISE images, we don't think this is misclassification per se. We think this is it being a lot more careful and being able to spend the time to classify all of the tiny little areas of continuous ripples, which the human just wasn't able to tackle. The opposite is true for the discontinuous areas. Our human mapper has kind of drawn a circle around a large area and said this is all about 20% coverage. Because the AI has gone in and picked out all of the different areas which are covered by ripples and the areas which aren't, it ends up with very low recall relative to the human, but very high precision, and that almost all of the time, I think around 70% of the time, it's getting it correct. We can see this when we look at a HiRISE image. So the gold is what the human drew, and the classification in green has found so many more tiny little areas which just didn't show up in the human view. The discontinuous is more similar, but whereas this has lots of tiny little meter scale patches in our AI classification, the human classification is much more solid blocks, and this is seen in the difference maps, where you get far more false positives in this case and far more false negatives in this one. However, when we agglomerate these and look at just all aeolian ripples, we see a much more similar pattern, although the AI has still picked out more fine detail. And in this case, we get usable precision and reasonable recall. So our conclusions are basically it works pretty well qualitatively. It's hard to compare quantitatively. AI mapping definitely has value, but we need to be very cautious in how we use it. We absolutely can use this extra detail that it provides, but we need to very carefully verify that it's not having difficulty in seeing boulders in one image. It's not thinking ripples are bedrock because they're a bit kind of more eroded and odd than the ones it's used to. We favor a combined approach where AI is used as a starting point, but then we come in and bring our human expertise to compiling the final maps. So this research has been published in several papers. This one in Icarus defines how we did the study, is our methods paper. Our colleague Eleanor Favaro then did some science using our data to map lots of aeolian ridges in Oxia Planum and interpret things about the aeolian history of the area from that. We have 2 map papers out so far, Jezero and Oxia, with more on the way. And that's where we'll leave it. Thank you very much.